the development of the midline, and I will divide my talk into the embryological part to try to go through the basic stuff and to try to simplify things as much as possible, and then we will move to the early neurosonography. So we are going to focus today on very small and early brain structures. Now, before we start, I would like to say that the information that I'm going to show you is only for educational purposes, which does not represent any official guidelines or legal standards, and you're not expected to perform these imaging and these ultrasound examination in your routine scan. This is for your to encourage you to learn more and to know more about the brain. Now, when I'm going to show you and I'm going to teach you some embryological landmarks and developmental steps, and if you are going to go deep, if you wish to learn deeper about the development of the midline, these are your tools. You should be familiar at least with these 2 textbooks and these 4 papers, and I'm going to go over, I'm going to show you developmental events which are based on data that has been published on these papers. And I think that no one can talk today about the development of the corpus callosum without knowing this fantastic pioneer and important paper from 1968 by Rakic and Yakovlev, which paved the way for us to understand how the midline structures and commiseration works. And then, of course, by Charles Ribot and Linda Richards and her group were the people who showed us the way. So these are at least the papers for you to start with. Now, in trying to simplify things, I will try to put it in a methodological way. So if you look at this illustration, this is a mid-sagittal cut. You have a left side view on a right hemibrain, and let's focus on these areas. Okay, these are the areas of interest, and I'm going to talk about a very specific time frame, which is around 10 to 14 or 10 to 13 gestational weeks, not embryonic weeks, because we are gynecologists, so it's easier for us to understand things in gestational weeks. Now, if we zoom in to this area, what we can easily see is we all identify the lumen of the third ventricle, and the reason we see the lumen is because we are cutting exactly through the mid-sagittal, through the middle of the neural tube. So the lumen here is the mid-sagittal area, and this is where the thalami and parts of the basal ganglia will develop on both sides. But along the wind line, you have the protrusion of the massa intermedia of the thalamus. Another important area for you to recognize is the Monroe, and for us on ultrasound, it's important because the Monroe is filled with fluid as opposed to the surrounder structures, which are non-fluid. So the dark hypoechoic area of the Monroe is a good landmark for us. And then we should put our eyes on the anterior-most wall of the third ventricle, the point where the neural tube has closed and it gives rise to the wall, the anterior wall of the third ventricle. Now, which structures we see here? If we divide this thin wall into, generally speaking, 2 areas, the ventral area, which is called the lamina terminalis, it's quite thin and small, and the upper, the more dorsal area, which becomes thicker and more prominent, this is an area that already hissed many years ago, called the laminar reunions, because this is the area that enables the continuation between the 2 hemispheres. It reunites the 2 hemispheres, so this is the laminar reunions, and this will become the commissural plate, which is a name coined by Rakic and Yakovlev. Now, an important commissural structure, the first commissural structures to develop in the human brain is the anterior commissure, and this is the lowest one. It comes from the area of the ganglionic eminences and from the peripheral areas of the brain, and this is at around 10 weeks already the fibers of the lamina terminalis can cross at the ventral-most part of the wall of the anterior wall of the third ventricle. Now, what happens just a few days later on, if we take this image, the area of the lamina terminalis becomes thicker, and the most important structures that we can already see between 10 to 11 gestational weeks are the fiber bundles of the fornix. These are 2 laterally separated fiber bundles. These are axons that connect between the hippocampal primordium, the early hippocampus, which is not where Prashant showed you yet at the temporal areas. At this stage, they are still along the midline, along the inner surface of the hemispheres, somewhere here, and with more deep ganglia, the septal nuclei, the lateral and the medial septal nuclei, and eventually it will go all the way to the mammillary body. So remember, these are axons that connect between nuclei of the hippocampal area and the septal area here, and they are crossing through the massa commissuralis at its lower part, at its ventral border here. So everything above the fornix will be now called the septum pellucidum. Now, just a few days after the fibers appear, the fornical fibers appear, around 20% of the fornical fibers will cross the midline to give rise to the second commissure of the brain, which is the hippocampal commissure. It will eventually connect between the two hippocampi in the mature brain, and this commissure can be seen crossing the midline at a little bit higher than the anterior commissure, which is at the ventral part of the lamina reunions here, the anterior lower part of the lamina reunions here. Now, once the fornices are here and the hippocampal commissure is here, all this cellular mass above or dorsal to the fornices, this is now the early septum pellucidum, and this has been termed by Charles Ribot in his papers. Now, what happens now in the next phase is a very important structure, because up until now I didn't say anything about the corpus callosum. Now, in order to give rise to the corpus callosum, there is a very important process which I will dedicate my next slide to, which is called the interhemispheric fissure remodeling. So if you're going through the interhemispheric fissure, you go to the lowest part of the interhemispheric fissure. At a certain point, you should reach a bridge, a cellular bridge, which is permissive, which allows callosal fibers to cross from one side to another. And this phenomena, which I'll explain what happens there, is very important, because if this does not occur, callosal fibers may reach the midline, but they will fail to cross, but because the bridge is missing, and then these fibers will be stuck on both sides, and this will give rise to the Probst bundle that we know from some of the callosal anomalies. Now, once the interhemispheric has undergone this remodeling and the proper cells have arrived in order to enable the permissive passage for the corpus callosum, now this area is called the massa commissuralis, and this is the important phase which allows the development of the corpus callosum. Now, another important part for you to understand that this whole cellular events and the massa commissuralis are developing up to a certain point, and this point is the border between the cortex, which develops in the inner wall of the hemispheres, and the septum pellucidum. So this is called the cortico-septal border, again a term coined by Charles Ribot. And nothing can go beyond, because beyond this point you have already the development of the cortex and the early cortical plate. But below the cortical plate, this is where the commissural fibers will develop. And the last part of these events are the pioneer callosal axons that will come down from the cingulate cortex. They will communicate with the supportive glial cells that I'm going to show you, and then they will be able to cross. So now, after the pioneer callosal fibers crossed, we come up with this configuration, which has the septum, or the primordium septum pellucidum. The lower part of the septum pellucidum is composed of two parallel fibers, which are the fornices, and a small amount of crossing fibers, which are the hippocampal commissure, and on the top of it, along the corticoseptal borders, this is the landmark where the corpus callosum cells will start, axon, not cells, axon will start to cross, and from here, everything will develop, and it will change the shape, but the configuration of who is ventral to who will stay like this, and this sets the final shape of the midline structures. Now, remember that I'm always saying septum pellucidum, but I didn't say the word cavum septum pellucidum or cavum septi pellucidum, because there is no cavum. This is one of the major points of my talk, to convince you that at early pregnancy you should not use the word cavum, because there is no cavum at this stage. Now, I mentioned the interhemispheric remodeling, so now let me show you this very important paper by Gobius and led by Linda Richards. And Linda Richards has published a lot of important papers which taught us a lot regarding how the commissural fibers develop. And what they showed in 2016, both on animal models and also on post-mortem human fetal imaging, is that in order for the massa commissura, in order for callosal axons to cross here, and this is an axial view of the I think it was a mice brain, you can see the callosal axon starts to navigate from along the interhemispheric fissure on both sides towards this laminar union towards the place they can join. However, at this point, they cannot do anything because they have no supportive cells. And what happens here is radial glial cells transform into multipolar astroglial under the influence of FGF8, and which influences the MAP kinase pathway. And these astroglial cells, they navigate to the midline, they intercalate into the mannings that are located deep in the interhemispheric fissure. They activate various enzymes like the MMP, for example, ethyl metalloproteasose. They disintegrate the mannings primitiva, and then they create a bridge, a permissive bridge. You can see here they intercalate into the interhemispheric fissure. They there's disintegration of the mannings primitiva here, and you have a stellar mass. This is the massa commillusuralis, and only these supportive glial cells will be able to communicate with the corpus callosum and to allow axons to cross. And as I mentioned before, if this fails to happen due to some kind of a genetic aberration, for example, and the cells are not able to transfer to multipolar astroglia, or they fail to migrate over there, the axons of the corpus callosum will be able to reach this point, but they will not be able to cross, and you may come up with various degrees of callosal anomalies or callosal dysgenesis. And in some cases, in those cases, you will also have the Probst bundles, which tells you that the development of the corpus callosum is not only about the axonal pathfinding or axonal navigation. This is only one side of the formation of the corpus callosum. The other side is the evolution of the midline, and the midline being able to communicate with these cells. And today we know that many genes that are associated with callosal agenesis are not associated with abnormalities of the axons, but with abnormalities of patterning and interhemispheric remodeling. Now, Charles Ribot summarized all of these events in a very nice, very important paper, and this is one of the illustrations from this paper. So now I showed you everything on sagittal images, but if you look at the coronal image, you can see here, this is the cortical border here, goes down all the way down here, and then the cortex ends at this point, and below this point you have the two lamina that will give rise to the septum pellucidum, but there is no fluid inside. It is filled with this cellular mass, the different glial cells, the wedge cells, the indusium grisum glia, and of course the zipper glia and the neuronal sling. And all of these cells are by expressing different genes of repellent molecule and molecules that resist axonal pathfinding, and eventually this whole massa commissuralis is located above the level of the fornices, above the level of the hippocampal commissure, and the lowermost structure, the ventralmost structure is the anterior commissure, as I showed you before. Now pay attention, I did not say anything about the cavum septi pellucidi at this stage. So again, at this point, avoid this structure. So once you understand this complicated configuration, you can understand why, when you look at the mature midline in adults or in children, this is what you see on the MRI, and this is what you see on the specimen. You see the corpus callosum, you see the septum pellucidum in adults, and Prashant showed it beautifully on his specimens. Remember that also Prashant showed it through the septum pellucidum. You have tiny vessels. These are septal vessels, septal veins. They are present there. They are flowing inside the septum pellucidum, and below is the fornix. You can see here the fornix, which is part of the structures that give rise to the roof of the third ventricle, together with the choriplexus, together with veins, together with the pia layer. But the most important thing for you to remember is that the fornices, they come from the hippocampus, they travel anteriorly, and then they give rise to the pillars of the fornix. They go down because they need to get to meet mammillary body, for example, here, and septal nuclei, and they do that on top of the Monroe. So actually, the roof of the foramen of Monroe is created by the fornical fibers that goes down, and you can see it very nicely here, also on the MRI with the third ventricle. The massa intermedia is here. This is a small massa intermedia. This is a big massa intermedia because this is a specimen, of course. Now, actually, when you look at the mid-pregnancy brain, mid-sagittal view at 24 weeks, you see quite similar configuration. However, we do not see the fornices so nicely like the MRI, and this is due to technical reasons and the beam reflection from the fornices, which is very low. and they are part of they are stuck together with all the surrounding structures, so we cannot actually see those bundles on the mid-sagittal view, but you can see here the anterior wall of the third ventricle, the massa intermedia, the echogenic tela choroidea, which is the choroid plexus at the roof of the third ventricle. On the MRI here, it's quite thin, but on the ultrasound, it reflects a lot of beam. And then you have the corpus callosum and the rostrum on top of the septal nuclei, which are here. And we know that the anterior commissure is somewhere here, but again, we don't really see it on the ultrasound. The anterior wall of the third ventricle and the floor of the third ventricle. Below this line, everything below this line is outside the brain. These are cisterns. So that was a very quick embryological step-by-step, how does the midline develop? Now the question is, okay, but what do we see and what do we not or we cannot see with a high-resolution transvaginal ultrasound early in pregnancy? So let's take a look at what happens from the sonographic point of view between late first and early second trimester. So this is an image that you all see in your routine scans. 12 weeks you are performing the nuchal translucency, but this is a high resolution transvaginal ultrasound through the anterior fontanelle. And let's go and try to teach you the pattern recognition of this structure. So the first thing you should recognize is that there's echogenic falx here, and the falx here is drawing the border between the outside area of the brain and the inner brain. So you see the falx here, and your eyes are looking what happens below the falx. So let's take away the falx, and now you should recognize the lumen of the third ventricle, which is here. Now let's take away the third ventricle. The next part for you to recognize on ultrasound, the easiest part to recognize, is the tela choroidea, which runs through the Monroe, because the anterior most part of the tela choroidea is the Monroe, because this is where the choroid plexus crosses through the Monroe into the lateral ventricles, and it is always hyperechogenic on ultrasound. Now, once you recognize the tela choroidea, you should take your eyes to the events that takes place anterior to the tela choroidea. So this is your area of interest here. Now let's take this thing off, and you recognize the thin area of the lamina terminalis here, and above the lamina terminalis, as you know, again, you know that the fornices are crossing here. We do not see them, but we know that this is the place that they cross, just above the foramen of Monroe, going down to the septal area, from up to down. So this is the area of the fornices, and anterior to the area of the fornices, we see the thicker cellular area, which is very nicely seen here. It has a different echogenicity from the falx, and this is the massa commissuralis, and this is where the septum pellucidum will eventually develop. Again, there is no cavum at this stage. Now, what happens just 1 week or 10 days after, approaching 14 weeks, again, we recognize the third ventricle, we recognize the tela choroidea and the hypoechoic area of the Monroe, because fluid is coming through the third lateral ventricles, through the Monroe into the third ventricle. And again, we put our eyes anteriorly, we take it away, and now we see the lamina terminalis, the anterior wall area. We know that the fornices are crossing here, we don't see them. We see the massa commissuralis, as I showed you before, but now, as opposed to what happened at 12 weeks, when you approach 14 weeks of gestation, you start to see this hypoechoic area here. I will take it away. You see the difference in the echogenicity. This is the corpus callosum. The very, very, very early fibers of the corpus callosum are crossing here, and when you approach 14 weeks, but this is a very, very small structure. But if you have a good insonation, usually you would see it at 14, 0, or 13 plus 6 weeks. Now, after you go over 14 weeks, towards 14 and a half weeks, again, you can see the falx very nicely, and then you can see the tela choroidea and the fluid that comes from the Monroe, the choroid plexus of the roof of the third ventricle. You see the massa commissuralis, the gray cellular area, and above this area, you can clearly see the hypoechoic fibers of the corpus callosum crossing from one side to another. Now, let's take the same fetus, and now let's see the corresponding coronal images, the perpendicular plane. So this is our landmark. This is the sagittal view, and if we draw a line exactly through the laminar units in the corpus callosum, we see that there is a cellular continuity. This is one structure that connects between the two ganglionic eminences and developing basal ganglia on both sides, and this area here of the laminar units and tela and lamina terminalis. And you can always see the hypoechoic fibers of the corpus callosum crossing, and above them is the most as the more echogenic area, which are the mannings stuck together at the bottom part of the falx of the interhemispheric fissure. And then you cross a line just a little bit beyond that through the Monroe and through the chori plexus. You can see the echogenic chori plexus. This is not the echogenicity above the corpus callosum. These are mannings, but here this is the tela choroidea crossing through the third ventricle, and below it you see fluid in the anterior third ventricle. This is the fluid that comes down from the lateral ventricles into the Monroe. And a few years ago, we published this paper where we described the normal development of the corpus callosum, and you are all invited to go over this paper. Now, I showed you 3D and nice images, but let me show you how does it look on the live transvaginal scan. So we start with 12 weeks, and again, you can see here the tela choroidea, the laminar reunions, and at 12 weeks, there's nothing much more to say. But again, please, there is no cavum septopellucidum. Don't say the word cavum. At 14 weeks, you start to see the corpus callosum starts to develop. You recognize the echogenic chori plexus, tela choroidea, and the border of the third ventricle, the lamina terminalis. And at 16 weeks, it's very easy to see the corpus callosum. It's just there, this hypoechoic area. And again, I would like to remind you, I didn't say any word about the cavum septipellucidi because already also at 16 weeks, as you can see here, this area is filled with supportive cells, the massa commissuralis. There is no cavum at this stage yet. Now, okay, so now let's reach the point. Let's go through the birth, or how does the cavum septi develop after you understand you have also all the genetic and the developmental and the sonographic background. Again, the sagittal and the corresponding coronal image at 14 weeks, you can clearly see here that there's the massa commissuralis here, and above the massa commissuralis are the fibers of the corpus callosum. When you go to 17 weeks, in most fetuses, you can still see the cellular massa commissuralis here and here on the coronal. You see the continuation between the two ganglionic eminences, and above that you can clearly see the corpus callosum developing. In sometimes, rarely, you may start to see at 17 weeks a little bit of fluid starts to appear, but after 18 weeks you can clearly see the early appearance of fluid replacing those massa commissuralis cells, which you can see here. So you see remnants of the massa commissuralis cells. You can see the corpus callosum, but inside this area now some fluid starts to appear. You can see it here by the blue color here. And in this area, you come up with two lamina of the septum pellucidum, and now you can call this area a cavum because there's a cavity, there's fluid that replaced the cells inside, and you come up with the cavum septipellucidi after 18 gestational weeks. And at 19 weeks, it's more clear because you recognize corpus callosum, the two leaves of the septum pellucidum, and the fluid inside. And in many cases, you have remnants of cells also in 20 or 24 weeks. These cells were already there to begin with. So this is how the cavum septi develop. So please, before 17 weeks, try to avoid saying you saw a cavum septopellucidum because it's just not there yet. Now, again, let me show you the transvaginal ultrasound clip. You recognize corpus callosum, tela choroidea, Monroe, and the cellular field massa commissuralis. And when you look at the fetuses at 22 weeks, sometimes you see strands or remnants, and you see this structure here. Now you can clearly see that there is a cavum septipellucidi, and inside these small strands are just remnants of vessels that were running here. I told you before, this is a vascular area. There are septal vessels here, and sometimes the cells disappear, but you may have remnants of atretic vessels. There's no flow in these vessels, but the strings are there, and sometimes you may have come up with leftovers of cellular tissue, and these are what you may call an obliteration of the cavum septi, but it's not an obliteration. These are cells that just failed to disappear or to be abolished. So actually, what I just told you has been described many years ago, at least by two papers. This is a paper from '82 from Singapore on rats, on animal models. You can see here that before the cavum septi appears, there is the cellular mass. These are the lateral septal nuclei, and because of some kind of cellular activity, which we're not going to go into now, the debris of these cells are being evacuated by phagocytosis, and you can already see here the remnants of the blood vessels floating here inside. These are the strands that I told you that you see on the ultrasound. So the phenomenon of evacuating and the appearance of fluid has been described many years ago. This is not something new, but it has never been described on in vivo observation in fetuses, and now we're just summarizing our data and hope you will be able to read it soon. And this is another paper from '88 by Hankin, and he showed very nicely that the death of the subcallosal sling, again, this is part of the cellular structures that support the crossing of the corpus callosum. When the death of these cells occurs and they disappear, you can see here that this is the corpus callosum. These are remnants of these cells, and eventually they disappear. You have a cavum appearing below the genu and the body on the splenium of the corpus callosum here, and this is the parasagittal section. This is not exactly a mid-sagittal section, but a bit parasagittal section. So this phenomena has been described many years ago on animal models. Now, in order to study this area, we cannot ignore some technical aspects which I would like to highlight. First of all, everything that I showed you is transvaginal ultrasound, but even if you perform transvaginal imaging, the angle matters a lot because different angles will provide different images because of different beam reflections. So these are two examples. On the left side image, this is a insonation through the posterior fontanelle. You can see very nicely the midbrain, hindbrain structures, but our interest now is on the midline area here, the developing corpus callosum, and you can see it much less clearly than the images I showed you before. And the same goes for a very frontal insonation. You can see here that the beam is projected through the bones, the facial bones, and you, in addition to the fact that you have a lot of shadowing, this area is far away from the probe, and many of the energy of the beam is being spread around, so you cannot clearly really see what I just showed you. However, my tip for you is always look for the echogenic telachoroidea, because of the high blood content in this area, you will always see the echogenic reflections, and this should be your landmark. So once you see the echogenic telachoroidea, try to mobilize the probe and the fetus, and use this as a landmark, and then look for the surrounding structures. Now, I cannot avoid saying something about the transabdominal image, because the transabdominal imaging, even today with the high quality, high resolution new probes, is still does not have the basic ultrasound physics, the basic resolution. Let me just show you. This is a 12 plus 6 days fetus, and you can see here that when you're insonating through the mid-sagittal, this is the image. However, I took the same fetus during the same scan, just moved to the transvaginal scan, and you can clearly see now the difference in the images. But most important thing is that please don't call this dark area here a cavum septi, because first of all, I'm showing you that there is no cavum. I hope I convinced you there is no cavum, there is no fluid at 12 weeks, so don't call this a cavum. And this hypoechoic area is because of the resolution is low and because the contrast is very high. So whenever you have reverberation or shadowing at this area even from vessels that cross there, you come up with this hypoechoic area, which might falsely give you the impression that this is a cavum septi pellucidi. Now, the problem is that many people are not performing a mid-sagittal section, but we all do axial images. These are the screening images. And when you do the 14, 15 weeks, and also if you do it with a very new machine, with the high sophisticated probes and all of these new filters, HD filters, and I will ask you, what do you see here? I think that most of you will tell me now, for sure, I see a cavum septi pellucidi, but please, I just showed you there is no cavum septi. What you see here are artifacts. This is the problem with the transabdominal probe. It will mislead you. This is not the cavum septi pellucidi, and if I want to convince you that this is not a cavum septi, what we should first do is move to the transvaginal probe. You should lower the contrast of the image so you get more gray shades, more level of gray shades, not only black and white. And we will start with the lateral approach. This is the axial view. And in order for me to make it easier, I will freeze the image, and I took some snapshots from the image to make it more clear. So if you start with the axial approach, you will always look, or you should look for a hypoechoic horseshoe sign, the horseshoe structure. You can see it here very nicely, this hypoechoic. But this hypoechoic usually is not because there is fluid, not because there is cavum, because these are the supportive cells of the massa commissuralis together with the corpus callosum that crosses. And if you want to understand it better, you should change the orientation of the probe. You should not insonate laterally, you should insonate perpendicularly through the anterior fontanelle. So this is what I did. I changed the orientation of the beam. Already when you are between axial and coronal, you can clearly see the hypoechoic horseshoe structure. But if you're insonating exactly through the anterior fontanelle and you lower the contrast of the image, you lower all the filters that gives you a high contrast image, and then you can come up with these three echogenic layers: the corpus callosum, hypoechoic, the third ventricle roof, the telachoroidea crosses through the Monroe, which is hyperechoic, and in between them, these are the massa commissuralis cells, which did not give rise to the cavum septum at this stage. So please don't call this a cavum septi pellucidi. Now, the last point which I would like to talk about, if we are talking about the early midline, is the pericallosal artery, because I know there is a lot of buzz about this issue, but please, you need to pay attention. When you look at the 17 weeks pericallosal artery, you can clearly see that there are two separated vessels, and only one of them, the one I show you here, is the one that actually crosses on top of the corpus callosum, and this is very easy for me to convince you that this is the pericallosal artery. Now, what's going on in 15 weeks? When you look at the 15 weeks, again, look at the corpus callosum, and you see there is a tiny vessel, which is the pericallosal artery, the tiny vessel that goes on top of the corpus callosum. And then you have another big vessel which is not touching the corpus callosum yet, and this is the one that sends the bifurcation, the falx arteries up there to the falx. You can see them here, but they are not coming from the true pericallosal artery. At 14 weeks, again, the same point, you recognize the corpus callosum, you see the small branch, which is the actual pericallosal artery, and above it is another branch, which is the callosomarginal artery, and this is the one that sends the bifurcation. And actually, if you look at 12 weeks, you see again, not the big artery that sends all its bifurcation, but only the small branch which touches the corpus callosum. This is the pericallosal artery. Now, to convince you and to teach you this point better, let's go to the 24 weeks and look at the pericallosal artery, what you all do in your daily scans. First of all, when you take a close look, and sometimes it's difficult to adjust the machine.
Roy, you need to finish.
Okay, sorry. So I will move on from here, and I just finished with this clinical example, and I will finish. So I'm showing you this 17 weeks image. This is an axial view. I recently saw a presentation by one of our colleagues. He showed the same case. And when I ask you, what is this? I'm sure that most of you will tell me that this is a case of absent septum pellucidum, right? Maybe it's even septo-optic dysplasia at 17 weeks. But my question is, are you sure? And the answer is no, this is not absent septum pellucidum, and in order to understand this, you need to perform a multiplanar imaging. And when you look at the multiplanar imaging, first of all, you see that there's a continuation of the cortex. So this is kind of a holoprosencephaly. And most importantly, if you compare the midline, this is the lamina, the massa commissuralis, the cells that were supposed to give rise to the corpus callosum, and they failed to undergo any patterning, and this is a straight communication between the two midlines. And in better to convince you, look at the pericallosal artery, and you see that the pericallosal artery is actually going on the anteriormost part of the brain. It's not going inside, so you don't have any patterning of the midline, and you compare the same age matched, you can see the pericallosal arteries run on top of a normal midline, which failed to occur here. So my take-home messages, and I'm sorry for taking longer, the brain midline structure developed gradually from late first trimester into the mid-second trimester. The cavum septi pellucidi emerges progressively and typically becoming apparent at between 17 to 19 weeks of gestation, following after the early corpus callosal fibers have crossed. Early assessment may lead you to false diagnosis of cavum septi pellucidi or other midline anomalies, like the example I showed you for the SOD, if you're not performing a detailed examination. Transabdominal ultrasound, even with the new generation probes, offer limited resolution, and especially it provides high contrast imaging.
עובד מושלם, מפה בגלל הקרבה לזה, זה עובד מושלם.
Pericallosal artery, please ensure that the correct artery is the one that's being identified before you decide and you make diagnosis based on some artery that you may think is the pericallosal artery, but actually probably it is not. And again, I apologize for extending my time, and I thank